Welcome back. The topic for discussion today is gas laws, as it's evident from the title. Now, the topic of gas laws does require knowledge from the material you have learned previously, and which includes colligative properties, your molar concentration calculations, and intermolecular forces, and everything else that you have learned before. So gas laws, the topic on gas laws is very much dependent on everything else you have learned prior to this. Now, there are two major types of gases. One is ideal gas, another is real gases. We're going to restrict the discussion to ideal gases for now, and if time permits, we'll come back to real gases. Okay. Now, what constitutes an ideal gas? So what I have here is a canister of oxygen, or a supply can of oxygen that you could get from commercially available, commercial manufacturers of oxygen gas. Say you get one of these canisters, okay? If this canister were to contain oxygen gas that behaves as if it is ideal, what properties does it have to have? An ideal gas molecules do not attract or repel each other. That is, each of these molecules in this container are behaving individually, that they don't influence the other molecule. The only thing that they would do is to collide with each other. Okay, that does not mean they're going to be attracted to each other or repelled each other. They just simply collide in the process of, generating pressure. Okay, so they do not attract or repel each other. And ideal gas molecules themselves do not take up volume. The total volume of this canister is extremely large compared to the volume occupied by a single molecule. We call them point objects. That means the molecule itself doesn't take up much volume in individual molecule, okay? But the volume of the container will be large compared to the volume occupied by a single molecule. All right? Now that's what constitutes an ideal gas, okay? Now there's a law that's written to explain this phenomenon of ideal gas more mathematically, and that is the ideal gas law, okay, which is PV equals nRT. Okay, you do not have to remember this, but I'm sure you will remember it in the process of doing some problems. Right now, each of the units in this equation have to be expressed in some constant universal terms. Okay, pressure is typically expressed in atmosphere, or ATM. Volume is expressed in liters. So if you were to have given a problem that contains volume in milliliters or other units of volume, then you must convert it to liters before you can actually use it in the problem. N corresponds to the number of moles. R corresponds to the gas constant, which again you do not have to remember. T is in Kelvin. So if you're given a temperature in degrees Celsius, for any of these laws that you're going to look at, you have to convert it to Kelvin before you can use. Now on this particular video, we are only going to summarize each of these laws quickly, and then we are going to try to do them in as little time as possible on the remainder of the videos, where we would come back and tie these individual laws to probably a real world application, and maybe do a math problem or two. All right. Okay, so that's ideal gas law, right? So P is pressure, V is volume, N is number of moles, R is the gas constant, and T is the temperature. Now Boyle's law. According to Boyle's law, pressure, okay, pressure is inversely proportional to volume, okay? Or volume is inversely proportional to pressure, okay? Inversely proportional means if one increases, the other decreases, right? So if pressure increases, volume decreases, and if pressure decreases, volume increases. Think of the air pump that you use to put air in a balloon, or in a tube, in a cycle's tire tube, etc., where the point where you bring the piston down, you're decreasing the volume because you're adding pressure But when you bring the piston back, then you're releasing the pressure, so the volume of the, the, the pump itself goes up, right? So that's Boyle's law, where pressure is inversely proportional to volume, or volume is inversely proportional to pressure. Okay, Shaw's law. Shaw's law is volume is directly proportional to temperature. Okay, or temperature is directly proportional to volume. What does this mean? This means that when your temperature goes up, volume goes up. When your temperature goes down, volume goes down. Okay, so temperature goes up, volume goes up. Temperature goes down, volume goes down. Okay, we could do some examples, and as I said, I'll give more detailed real-world applications as we do these concepts, because I want to keep this entire summary video to just one video. All right, now Gay-Lussac's law, where is pressure is directly proportional to temperature, or temperature is directly proportional to pressure. Okay, get a different color. Okay, what this means is if temperature goes up, pressure goes up. If temperature goes down, pressure goes down. Okay, Avogadro's law. Okay, what does Avogadro's law has to say? Avogadro's law compares volume versus volume is directly proportional to the number of moles, or number of moles is directly proportional to volume. That is, if N goes up, V goes up, N goes down, V goes down. And this is nothing but you trying to blow up a balloon. If you put more air, which is number of moles, then the volume of the balloon goes up. If you put less air, then the volume of the balloon is relatively small compared to the situation where you put more air into the balloon. Okay, Dalton's law, which is, I'm going to write just the generalized law here, which is the total pressure of a system equals pressure of all individual systems. Pressure of system 1 plus pressure of system 2 plus pressure of system 3, etc., 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 etc. Right? And Graham's law is rate of diffusion, which is rate 1 over rate 2 equals inverse of square root of m2 over square root of m1. Okay, I think this would make more sense when we do more mathematically, but what does Graham's law states is, let's say you have two gases, gas 1 and gas 2. Okay, if gas 1 has a molecular mass of say 100 grams per mole, and gas 2 has a molecular mass of say 150 grams per mole. Okay, R1 is the rate of effusion. What is effusion? Let's say you put these two gases in two balloons. Okay, so this contains G1 and this contains G2. Okay, let's put a small hole in the balloon in both of them. Okay, effusion is when a concentrated gas or substance escapes through a fine hole into a larger volume. Okay, if this balloon were to be placed in say a canister, okay, the volume of the canister is much bigger compared to the volume of the balloon, so the gas would have to expand into this larger canister, okay, through this fine mist. Okay, so this is called effusion, that is escaping tendency of a gas through a fine hole from a smaller volume to a larger volume. Okay, that's this rate. R1 and R2 are rate of effusion, that is how fast an effusion can take place, and M1 and M2 are the molar masses. Okay, M1 and M2 are the molar masses. If you notice, R1 is not directly, it's opposite, right? And R2 is opposite to M2. That means rate will decrease if molar mass increases. So which of these two gases would have a higher rate of effusion? Well, gas 1 has a molar mass of 100, gas 2 has a molar mass of 150. And I said if molar mass increases, rate decreases. So that means gas 1 would have a higher rate of effusion over gas 2. Okay? So these are the several laws that govern the property of gases, and I have summarized all of them in this one single video. Now, in the successive videos, I'll try to do 2 laws per video. That way, I can keep the total number of videos to like 3 or 4 for the topic of gas laws. But then I'll give you some real-world examples, and we can wrap it up with a math problem. All right? So stay tuned.